Hello everyone, welcome to my video. Myself Kem Shang, studying in Sri Venkateswara College of Engineering in Information Science and Engineering Department, first sem. Today I am going to explain conduction of heat using maths. Uh, in this video, let's get started. Conduction of heat in maths. Introduction to heat conduction. First, let's understand what is heat conduction. Heat conduction is the process through which heat energy is transferred within materials. This transfer occurs due to temperature differences moving from hotter to cooler areas. Understanding heat condition is essential in various fields including engineering, physics, and mathematics. The mathematical model. The heat conduction process can be described using Fourier's law of heat conduction. This law states that the heat transfer rate is proportional to the negative gradient of temperature. Mathematically, it is expressed as Q is equal to minus K by lambda T, where Q is the heat flux, thermal is K is thermal conductivity, and lambda T is the temperature gradient. Here we can observe there is a temperature 1 with an object with temperature T1, object with temperature 2. The heat is transferred from one of the object to the other object, that is from outer object that T1 is greater. It is mentioned here. Let me show it. T1 is greater than T2. T1 is greater than T2, the heat is transferred from hotter object, that is hotter region, to the cooler region, and material having thermal conductivity, that is represented as K, and the area covered is area A, represented with capital letter A. So X is the distance between the two objects where the heat is transferred in between. From this we get the mathematical expression Q is equal to minus K by lambda T, where Q is heat flux that I have already explained. Next, let's go to the heat equation. The heat equation is a partial differential equation that describes the heat distribution over time. It is given by fraction partial differentiation of U with T, that is dou U by dou T, where U is the temperature and T is the time and alpha is the thermal diffusivity. This equation is fundamental in thermodynamics and is used to solve various heat conduction problems. The heat diffusion equation is parabolic partial differentiation that describes the distribution of heat, that is variation in temperature from one region to another region in a given time, starting with heat diffusion equation in cylindrical coordinates. This represents the cylindrical coordinates. Uh, Derive an expression for the temperature as a function of the distance from the center within a pipe after. The pipe has constant thermal properties K and alpha. K and alpha are the constants of that constant that represent thermal properties of the pipe, and as a uniform thickness of T, there are no generation process occurring within the pipe. The conductor has length L and the diameter D. The temperature at one end of the pipe R is equal to R1 is held at T1. The temperature at the other end R equals R2 is held at T0. This justifies the derivation. Let's move on to next slide. Boundary conditions. Boundary conditions are essential for solving the heat equation accurately. Common types of boundary conditions include Dirichlet, Newman, and Robin conditions. These conditions define the temperature or heat flux at the boundaries of the domain, influencing the solution of heat equation. Steady versus transient heat conduction. Steady state heat conduction occurs when the temperature distribution does not change over time. In contrast, transient heat conduction involves time dependent temperature changes. The mathematical treatment of these two types of condition requires different approaches and solutions. 1D heat conduction. 1D heat conduction simplifies the analysis by considering heat transfer in a single direction. The heat equation for one dimension is given by partial differentiation of U by T and is equal to alpha into fractional double differentiation of u and t. This model is commonly applied in situations like a long rod being heated at one end. Numerical methods for heat conduction. Numerical methods are often employed to solve the heat equation when analytical solutions are different or impossible. Techniques such as the finite difference method and finite element method discretize the equations for computational solving. These methods allow for the simulation of complex geometries and boundary conditions in heat conduction problems. These are heat flux vectors which are represented here. The heat transfer. Applications of heat conduction. Heat conduction is widely applied in all the fields. Its principles applied in designing thermal insulation materials are the major ones. Engineers use heat conduction analysis in electronics to prevent overheating of the components. The study of heat conduction also plays a crucial role in environmental science, particularly in understanding heat transfer in soils and bodies of water. Challenges in heat conduction analysis. Analyzing heat conduction can be complex due to factors like material heterogeneity and phase changes. Due to the differences in the materials from one material to the another materials, there are different properties of that materials, which makes it complex to analyze the heat conduction properties of that materials, and automatically the phase will change of that material. Non-linear materials and varying thermal properties further complicate the mathematical modeling. As I said earlier, the same thing, the thermal properties of the different materials complicate the process of analysis. Ongoing research in heat conduction aims to develop more accurate models and solutions for these challenges. Conclusion. uh, Understanding the conduction of heat through mathematical modeling is vital for numerous practical applications. The interplay between theory and numerical methods enhances our ability to predict and manage heat transfer. Heat transfer can be majorly used in the components, as I said earlier, in its applications. So we have to mix it there with the theory, and also we have to solve the numericals over the this concept, and continued advancements in this field will lead to more efficient designs and technologies in features. Thank you.